G'day, welcome to the second part of our uniform circular motion discussion. At the end of the last video we derived the centripetal acceleration as the change in velocity over the change in time and saw that that has to be directed radially inwards. Alright, so delta V is radially inwards, therefore the acceleration is radially inwards. What we're going to show you now is that there is another formula for the centripetal acceleration in this particular case that can be derived from similar triangles. So let's have a look at that. So you can see from this sketch here from the last video that we've got our change in velocity here, the final velocity minus the initial velocity added together by vector subtraction. So we're adding the negative of V naught, and we can see that delta V is radially inwards. So we end up with a triangle there like that. And what I'm going to do is redraw the circle, which I've done here, and this is the initial point of the velocity and this is the final point. And in fact there is a displacement between those 2 points. Okay, and of course you would consider the limit as the displacement tended towards zero if you were actually considering this mathematically, but just visually you can see something from these 2 triangles. So as the velocity, or as the object, which is going in a circle, remember, as it goes from the initial point to the final point, it can trace out a displacement delta S. Now I know that that's a straight line and it is actually going in a circle, but as this gets smaller and smaller you can see that delta S will actually approximate the travel around the circle. So we need to realise that as that happens there is an angle theta traced out by that path, and you can hopefully see that the angle in here is also going to be that angle theta. If you want to see that a little bit more clearly, just imagine that we let V0 and V0 come closer and closer together, and you can see that both of these angles, this one here, will start to approach zero. So as these two closer and closer to each other, this angle will approach zero as well. So what we've got here is similar triangles. Okay, we've got a common angle between them, and we've got 2 side lengths the same here, that's the radius, and 2 side lengths here, which is the velocity. Remember, we're talking about a constant velocity here, so V and V naught have the same magnitude. From those 2 similar triangles, you can actually get this relationship. Delta V divided by delta S has to be equal to the side length here divided by the side length here, which is the speed divided by the radius. Okay? We also know, however, from our formula relating velocity displacement over time, that the displacement is equal to the velocity multiplied by the time. So what we're going to do is substitute this back into this expression here. Okay? Then we're going to bring the velocity over to the other side. From here to here, we're going to multiply both sides by V. And we get this expression V squared on R. Of course, hopefully you recognise this now, delta V over delta T as the acceleration. So we end up with this formula here. Okay, where V is the the tangential speed of the rotating object, and r is the radius of rotation. And this is actually a formula that's very specific to rotating objects, and therefore we call it the centripetal acceleration. Okay? Hope that makes sense.